last time we met, I showed you this slide of the bottom of a sedimentation tank and all this sludge, and that it was anaerobic and that it stank. And I wanted to add this reflection, and that is, as engineers, it is very, very tempting when something like this happens, and when a system ends up perhaps not being maintained by the community because of these kinds of problems, that as engineers, it's very tempting to say, oh, that community didn't maintain the system that we provided for them. And I just want you to be aware that when you hear a statement like that from an engineer, all of your red flags should go up, and you should be saying, wait, that assumes that what the engineer did was just fine, and that all the problem is with the community. And maybe the community made a rational choice to not maintain a system that didn't work, because that is actually a very, very common occurrence. There are many, many cases where technologies get installed, they don't actually work, the community doesn't maintain it, but the community is blamed as if they were the one that didn't do the job right, when actually, even if whoever had been in the community, the same decision would have been made that it wasn't worth maintaining that technology. So things to ponder. So let's go on. This is another problem that happened in a water treatment plant. This is a view of the two sedimentation tanks looking in on the plate settlers at Agalteca. And the problem was that there were a lot of flocks coming up at the one end of the sedimentation tank. And I know that the image is not great, so I'm going to draw squares around what I want you to see. Look at what's right there. If you look really closely, that is two plate settlers laid on top of the plate settler modules to prevent any water from coming up through those plate settlers. That's pretty puzzling, right? So the reason that they did this is because there were flocks coming up through those plate settlers. And so as a rational solution, they blocked the flow through those plate settlers. And then I want to draw your attention to what I've written on the left there. For many plants, it is common for the water in the middle of the tank to be clear, yet have a lot of flock rise at the end of the tank. And then that indicates density flow. And the solution is to block off the last 10 to 20 feet of the tank so that the flocks can't rise. And that comes from this textbook, which is like a top textbook that's used by consulting firms in designing water treatment plants today. And I want to point out that it's wrong. Okay, what happened is they assumed that it was a density flow when actually it's not. And I also want to point out that this textbook recognizes this problem, and they don't actually have a solution for how to design the SED tank so that this problem doesn't occur. So now I want to show you what we learned. So we ran into this problem, and this became a student design project to try to figure out what was going wrong in this tank. And they actually built a tiny little model of a sedimentation tank with the same kind of piping to go get the water in and get the water out. And they ran dye through it, and there was this big aha. And here's where the big aha comes. So this is looking at the side of an Agua Clara tank. And in this tank, the water enters in this pipe. This is the inlet channel. This pipe stub would normally not be there. And so the water's entering in that channel, going down through this pipe, which connects over here. And then all along this inlet manifold, there are holes in the bottom of this pipe. That's a kind of conventional design for distributing water into the bottom of these tanks. And it looks great. And it looks like it's going to do exactly what you want. And think for a second, the water that's coming out of the holes, there's holes. You can just barely see them, but there's holes in the bottom of this pipe. The water that's coming out of those holes, where does it go? So the pipe's coming in, it's in the bottom of the tank, near the bottom of the tank. There's holes right out the bottom. What direction does the water go? I think the obvious answer is down, right? And you think it goes straight down, right? Because the holes are like pointed down. And that's what I thought. But the water doesn't know that that's what it's supposed to do. And the water just does what's easiest. And so the water does this. Ooh, is that an insight? The water has velocity inside that pipe, and that velocity doesn't just go away because it comes to a hole. It maintains that velocity as it ducks out the hole, and it continues to have a horizontal component of velocity as it goes through that hole. And that means that in the bottom of this design of a sedimentation tank, which is what we had at Agua Azteca, there's this big flow path. Because water doesn't go where you want it to go, it tries to go in a straight line, right? It has inertia, it wants to go straight, and it goes straight until it can't. And so it goes straight until it runs into that concrete wall at the end of the tank, and then it turns up. And here's another key insight. Plate settlers provide almost no resistance to flow. There's no head loss. There's a tiny bit of head loss, but it's measured in, I think it's measured in micrometers, i.e. it's negligible. So the water just flows right up through those last few plate settlers. And so what they did at Agua Azteca is they put a block on top of those plate settlers, and that prevented the flow from coming up through those plate settlers. You see how this worked? So if you're going to solve this problem so that it doesn't happen again and you don't have to block some of your plate settlers, what do? And you have to go back to what was the origin of the problem? The origin of the problem was that the water coming out of the orifices didn't go straight down. It had a horizontal component of velocity. So that's what we have to fix. And it's not about a density current. It's about kinetic energy. So, well, that's what we would like to have happen. We'd like it to go, actually, no, that's what the plate does on the top, but that's still a lousy solution. So insight that this is an inertia problem. This is an early attempt at solving this problem. So you see those straight pipes stuck on the bottom of the inlet manifold, and some early data suggesting that that switch actually improved performance of the sedimentation tank. So the orange data points are from an earlier system. Actually, this is for an even earlier system that also had problems. Maybe the point here is that the improvements that we've made did actually make an improvement in the performance of the plants. This is the new design for the manifold for the inlets at the bottom of this sedimentation tank. And I'll show you a couple pictures of how that's done. So the addition is those straight, what we call diffusers, that straight pipes that straighten the flow and create a nice jet at the bottom of the sedimentation tank. So this is where the water leaves it. Let's start at the bottom. This is where the water enters the sedimentation tank going into the inlet manifold. Here's the flock weir that controls the level of the flock filter in the bottom of the tank. Back in here is the flock hopper. That's where the flocks consolidate, and they do form like a liquidy sludge that then is wasted by opening up a valve. And on the left, you can see the whole bottom of the tank, and then I'll add the inlet manifold in here. So there's the inlet manifold added in. And let's look at how they fabricate these. So here they are fabricating one of these systems. They've got a drill press and they're drilling holes in the inlet manifold. I'm just realizing there's holes on the other side of that inlet manifold So this must have been a posed picture. I had never noticed this before, right? The holes are on the other side. So anyway, presumably he's not drilling a hole right now. But the holes on the other side, the hole diameter is equal to the inner diameter of this mold. And this mold is used to slightly reduce the outer diameter of the diffusers that get plugged into that pipe. But it's just standard pipe that they take and they mold both ends. One end gets smaller so that when you plug it into the manifold, it goes in so far and then stops. It goes into the place where it gets larger in diameter, and so that makes it easier to glue it in and have it actually stay. Any questions about that? That's a finished product. So now the water comes out straight. So these have to be long enough so that the flow gets straightened and there's no horizontal velocity component anymore. And then this bottom part, and notice that this inlet manifold is not centered over this jet, it's off to the one side. Or it's a 3-inch PVC pipe cut in half, it's off to the one side. You might not be able to see that real clearly in this photo, but it is true. And then just this notion that we keep on learning. So in the early designs, we had a drain below this yet. So there were holes in the jet reverser to a drain pipe that was below that. And we very quickly realized that was completely unnecessary, and the jet reverser can be the very bottom and there's just a drain at the end of the tank, and that's all you need. So why did we flatten the tubes? And it's because we need to have any flock that slides down this slope has got to be picked up again. So we can't have any gaps where there's no water coming down in a jet. So if there were a gap between jets, then sludge would accumulate between those jets. So we need to have water coming down in a continuous jet the entire length of the sedimentation tank so that all the flocks get picked up. Did that make sense?
Yeah, that's perfect.
Okay. Other questions?